This is Mr. Sindel bringing you a custom design lesson about real-world approximate fractals. So let's read. In 1967, mathematician Benoit Mandelbrot asked a simple question: how long is the coastline of Britain? At first, it sounds like a fact you could just look up, but different sources gave wildly different answers. Why? Because the answer depends on the length of your measuring stick. If you trace Britain's edge with a 100-kilometer ruler, you skip over all the bays and inlets and get a short coastline. If you switch to an itsy-weetsy teeny little 10-kilometer ruler, you're forced to follow more detail, and the total length gets much longer. Shrink the ruler again, and the number only keeps growing, at least in theory. Mandelbrot realized this wasn't a mistaken measurement, but rather revealed a deep truth about nature. Coastlines don't have a single fixed length because their jagged shapes repeat details at many scales. This insight gave rise to the field of fractal geometry, which tries to measure how rough or how space-filling a shape really is. The coastline of Britain became the classic example of how fractals show up in the real world, and why today we measure not just length or area, but also dimension to capture the complexity of natural forms. There are two activities in this packet. The first activity is using the coastline paradox and actually trying two different measuring sticks. The second activity will be estimating fractal dimension using grid sampling or box counting. Let's jump into activity number one. So we are given a map of a coastline. What we're going to be doing is looking at the coastline of California. And just as a way to remind everyone, for California, we have the coastline on the left or the west-hand part of California. There are dividers between other states over on the right, top and bottom side. So those don't really count. And it's jagged over here, but it doesn't count. So the coastline is everything up here. And technically, coastline is defined as any part of California that touches the sea. Technically, these islands are part of California and they touch the sea. So if you can, try to incorporate those into your calculation. However, much more traditional methods only measure contiguous, or things that are part of California's main coastline. So it is up to you and how you want to define that. So I'm going to be using circles because it's really hard for me to have a line using my application GoodNotes. I am first starting out with a circle that is roughly 100 miles long. So what I'm going to do is I'm going to grab my circle and I'm going to pull the circle up to the very top. What I would recommend for everyone following this activity is to have, I didn't realize I could grab just the inside part of it, is to grab like a paper clip or a stick or anything. What I'm doing is I'm eyeballing something that is on the edge and then on the opposite edge through the center of the circle. So what's a diameter? So let me show you something that would be incorrect using my technology. This is something that would be incorrect. While yes, one part is on the edge, this one part isn't through the center. It's not a diameter. So I have to be really careful about how I position my circles here. All right, so I'm going to go ahead and say that that is roughly one of my circles. And then I'm just going to copy and paste a bunch of these so you can kind of see what I'm seeing. So I should grab things correctly and say that that's probably the next one. And again, I'm kind of eyeballing from here to there for the next one. And you're just doing this over and over again. Notice that when you're going over this bay, I have to skip over the bay because of how how big my measurement tool is. I have to go from here all the way down here for my straight line. And then I'm just going to keep copy pasting. Say right about there. And this is where I have to make that decision of how do I incorporate these islands. And I'm choosing for the large measurement tool to not incorporate those. It's just too hard. It's inaccurate. I'm not going to have that. So sorry, islands. Oop. There. And yeah, this is the weird part. So a lot of students ask, well, what do you do with this little bit? It's up to you. That to me, that looks like maybe half of a circle. Here, let me go ahead and put this circle and see. I'm going to say it's about, I don't know, maybe a third of my circle, maybe a quarter of my circle. It's really hard to see. But with that larger measurement tool, Let's go ahead and count. We have 1, 2, 3, 4, 5, 6, 7, 8. I'm going to call that a quarter, 8.25. So I'm going to come to the front side and say that was about 8.25 of those steps, and my measure length was about 100 miles. Again, your measurement might be a little bit different than mine. I try to come out to exactly 100 miles because it makes the multiplication much easier. I just move the decimal place, the number of zeros, in this case 1, 2 to the right, and this is 825 miles. What happens if the measuring stick is a little bit lower? So now I'm going to erase all of those. And I have pre-measured out some circles for this lesson. I'm going to put the circles right there. You can see that there are 4 circles that fit in my 100 miles, which means each of these 1 circles is about 25 miles. So if I'm going to come back over here, I'm going to say my new measuring stick is 25 miles. And let's count the number of circles that this is going to take. This is going to take me a long time because the last one already took me a bit of time. So stick with me here. I'm going to go from the bottom to the top because I already have my circles. And it's okay if this is not precise. I'm just going to go kind of fast here. All right, so I have what I think is a really close approximation. Let's go ahead and count how many circles I have. Notice that in this case, I did get into the base, so I got a little bit of extra detail. Let's count the number of circles. Oh, and I also do have islands in this case. I excluded this one. It didn't really fit the circle that I had. All right, ready, set. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37. We'll come back to the last one, 38, 39, 40, 41, and I'll call that 41 and a quarter. So 41 and a quarter, that's going to be 41.25-ish. And I do need a calculator for this. So calculator, help me out, please. I have 25 and I multiply the number of lengths, about 41.25, and I get 1,031.25. 1,031.25, and that's to be expected. I'm expecting this number to get larger every time that my measuring stick goes down in length. Cool, that's the end of the first activity. So the second activity is much more interesting, at least to me, because you can actually calculate the fractal dimension, at least approximate it. So what you have is you have, again, the same map of California. I'm going to erase all these circles, all this hard work. And what I'm going to do is I'm going to take one of these large grids and I'm going to overlay it on top of this map of California. So let's go ahead and do that now. That's a small grid. There's our large grid, and I do want it to be the correct size here. Oop, that's not what I wanted to do. I wanted to grab you. Let's see. There we go. Make this right about there. The Made by Mr. Sindel kind of lines up if I have it correct. Made by Mr. Sindel almost lines up. It's close enough. The main thing is that you have a grid that is, it does need to be a little bit bigger. Whoa, don't know what happened there. Wait, what happened? It's, technology is being challenging. Okay, there we go. So what I'm doing here, and it doesn't really matter how you put your grid, as long as it's the correct size, which won't happen incorrectly in the real world. I usually give you a transparency of this screen, so it's really easy to overlay. I just am having technology issues. So what I'm going to do now is I'm going to count how many squares the coastline takes up, even if it's a little bit of a tiny piece. So what would be an example? So you guys see this piece right here, even if it's a little tiny piece, that still counts as a square with coastline. So what I'm going to do is I'm going to count up all the squares. Let's go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. And then the islands are really fun because they always are in here, right? 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. And I don't know, does that one count? I don't think it does. I'm going to say it doesn't. So it's going to be just 36. So you can say when I overlaid the large grid, the number of intersections of the coastline of California, there are a total of 36 large squares. So you come back over here and say, how many squares did you count? I counted 36. And then you do this again for your medium and small grids. So again, I don't just have, let me go ahead and erase all this stuff. Grab all of you and delete and delete. There you go. I also have a medium-sized grid and a small-sized grid. And just in case there's mathematicians that are really scrutinizing, like, how did that grid work? This one size square right here is the same as this one size square right here, which is now, there's 4 squares in here, which is the same as this 8 by 8, however many 8 is. I don't know. I can count 1, 2, 3, 4, 5, 6, 7, 8. So like a square, I assume that's a square. That one square is the same. You just keep doubling the side length, or you keep multiplying the number of squares by 2. No, that's not right, because it was 1 square and then it turned into 4. I think you keep multiplying by 4, right? That makes more sense. All right. So now let's do it again with the medium-sized grid. Right about there. And I don't want to actually label them. I'm just going to go ahead and count by tapping. So highly recommend, if you're tapping on squares, double tap every 10. And I'm noticing that I have this issue of that should have been a square. If this was a square there, that would count. So that is going to be one of the squares that I'll be counting right there. And it doesn't matter if this grid is rotated or whatever. It should still work no matter what. So I'm going to go to my highlighter tool. I'm going to be quiet as I count some squares. Notice how I just did a double count. All right, I finished counting and I got 74 squares. So let's go ahead and add that as well. 74 squares. And then finally, you have to do the same thing for the small number of squares. And I know that there are students that are like, oh my God, that's so much work. Can I just like multiply by 2? Because that's almost what it is. No, if you multiply by 2, then what you're saying is that it has a fractal dimension of 1, and that won't, I mean, sometimes it is a fractal dimension of 1, but most commonly the fractal dimension is going to be above 1 for every coastline. So time to do it for the next size square. So grab all of you, delete, and the final one, this is the one that's scary, the small grid. All right, I highly recommend using that strategy of double tapping. If you're drawing with pen or marker or something, every 10, that way you can keep track if you lose count. Ready, begin. Whew. All right, that was 176 squares. All right, and finally, we need to calculate the fractal dimension. So the way that we do that, I don't have the instructions on here, but I can show you what you should do. You need to have, it doesn't really matter if it's, I think a graphing calculator is the easiest way to do this. I'm not going to use any part of the graph. I'm just using the table feature of the graph. So I'm going to have a table. I'm going to say that it's going to be large is a 1, medium is a 2, and small is 4. Just multiplying by 2, multiplying by 2. And then the number of squares is 36, and then 74, and then 176. And then I need to take the log of each of these. So I'm going to create a new variable called x2. I'm going to say that that's the same thing as log of x1, so log of x1. And then I'm going to say a new variable y2, which is going to be the same thing as log of y1. And then I'm going to do a linear regression using just y2 and x2 instead of x1 and y1. So I'm going to say y2 here is going to be, where's my tilde key, is going to be doing a linear approximation with mx plus b, right? So I'll say mx plus b. The only problem with this is it's not mx, it's mx2. Remember, you have to use your x2 data. So you say mx2. And yeah, my fractal dimension is way off, but that's okay. It's just for demonstration purposes. So notice what my slope is. The slope is your fractal dimension in this case. So I can say that my here, I'm right-handed, so let me move up on this side. I can say that my fractal dimension using just 3 points is the slope of 1.145. And this is wrong. Based on all the estimates that I've seen online, the fractal dimension of California is much lower. It's around 1.05, 1.06, somewhere in that region, although you should probably fact check me on that one. I'm relying on information that's very old in my memory, over a week old, and I can't remember the exact dimension. But that does conclude the real-world approximate fractals worksheet. All the other pages in this worksheet were simply all the large grid, medium grid, and small grid that you can overlay with transparency sheets over the coastline of California. Hopefully, if you are a teacher looking at this activity, I still need to answer some questions. You can do your own coastline. You don't have to do California. You can do some other random one. You can do Norway. That's a really famous one too. I'm sure that we want to do some discussion questions as well. Let's dive straight into those. So, number one, in the perfect math world, fractals keep repeating forever. But in the real world, detail eventually stops. For example, the scale of atoms. Why is this different and important when we study natural fractals like coastlines? And you want to say something, well, you can respond to this however you would like. But my first instinct is, with math, you can have a measurement tool that is almost zero. Like if you have calculus, you can basically take the limit as that measurement tool goes to zero, which would have a coastline of nearly infinity, or basically infinity if you can take the limit as you approach zero. But there is a cutoff in the real world, meaning you can't get to infinity in the real world because atoms stop you, and you can't get any smaller than that. You can't keep getting closer and closer to zero. You can't get smaller and smaller. Number two, and this is kind of a straightforward one. What happened to your coastline when you got smaller and smaller? So what was supposed to happen when we got smaller and smaller, when we went from here to here, was our coastline estimate was supposed to get bigger. And that is what happened to mine. I was being very careful. Maybe you're not being careful and yours didn't get bigger, but mine got longer with a shorter measuring stick. And this one these are my favorite questions. 3 and 4 is kind of like those meaty questions that I really, really care about. So check this one out. So these are some of the numbers I've been pulling. Like the CIA World Factbook for Norway's coastline is 25,000 kilometers. The Norwegian Mapping Authority says, no, it's 100,000 kilometers. And there's other detailed chart estimates that I've looked up online that say that it's over 250,000 kilometers. I mean, look at the difference between 25,000 and 250,000. They added an extra zero. They multiplied this one by 10 and said, no, that's good now. And this is what's known as the coastline paradox. This is like the main one, right? So why? What's going on? So you mainly want to say here that different agencies used different measurement sticks or measured tools. Some of them look at a map and they measure every 100 kilometers. Some of them measure every 1 kilometer. Different tools will give you different results. If you have a really short tool, then you'll get a really long result. And the most interesting question of all is this. So I try to find a really smooth fractal. So if you look at South Africa, it has a fractal dimension between 1.05 and 1.08 by everyone's estimations. Whereas Norway, from question 3 up here, all of these numbers were really different because its fractal dimension is much higher. It's 1.3 to 1.4. So look at all of the facts about South Africa. Is there a lot of disagreement like you do with Norway? Well, let's find out. Well, the CIA World Factbook says it's around 2,800 kilometers. Wikipedia says 2,500. And then the government description from their official website says it's a little over 3,000, which are all really, really close together. Why are all those so close together when it has a lower fractal dimension? Lower fractal dimensions, you can interpret that as saying that there's less discrepancy between your measurement tools, right? So that's how I would say. I would say lower fractal dimension is associated with lower differences in final length calculations, even with different lengths of measurement tools. And you can go even further on that. You can say, because it is smoother and there's not a lot of detail, and by detail I mean like coves and bays and et cetera, right? Bays, et cetera, that get overlooked with large measuring tools. Nice. All right, we've answered all the questions. I've demonstrated all the pieces of this. Thanks for watching.